Here we go. I found the right key to push. Now, there are two books you can use for this course, and I sent you something yesterday. Did you get it? That you can get these with 50% off? Anybody get that?
Yes.
Okay, good. These are two books by yours truly. One that's more, it's a small, just a half-inch thick book. Introduction to what's sort of my thing, energy return on investment. And with a focus on both the science, the economics, and the sustainability. And the second is a textbook on what this course is about, an introduction to biophysical economics. So if you want to, you can go to Amazon, well, use that thing I sent yesterday and get these for 50% off. I don't know what that should be, 25 bucks or 30 for the red one and 50 odd for the orange one. And you can get whatever I lecture about, you can get in enormous detail in these books. Okay, now the objectives of this course. The first is to understand the earth around us. And understand that in terms of energy. Now, we are not trained, excuse me, we are not trained to think about energy too much. We're told that energy is something that exists in the physics lab or something like that. But my focus is that energy is part of everything we do all the time, and we have such an abundance of energy, we don't think about it. But I want to help you all think about it. I would like to honor those who helped us understand how the world works, show the role of energy in natural science in understanding contemporary events, unmask the insanity of contemporary which is called neoclassical economics, and to prepare for the future. I guess I didn't make that 6, but that's what it should be. Now, excuse me, I think there might be somebody else waiting to be admitted. So I don't know how to go from this to, yes, see if there's anybody else wishing to be admitted. All right. Okay. So, are you all with me again? You can see my slides. Did somebody say yes or no?
Yes.
Yes.
Okay. So in fact, energy is part of everything we do. And just for an example, take the kitchen. We may think about energy when we boil water or turn on the oven, but who thinks of a sharp knife as energy, as a force concentrating device? Of cooking as a means of giving the human gut access to plants whose cell walls, which most plants are made of, we can't digest until we cook them, and so forth. Or page down, come on. Oh, it stopped working. Who thinks about dishwashing in terms of energy? I'm thinking about energy when I wash the dishes. The force of the water coming out of the spigot, and in terms of pushing the dirt off the dishes, the hot water doing so much more work, the scrubbing of myself, and my favorite energy, which is Gibbs free energy, which is you take a pot or a pan that's got all kinds of stuff stuck on it and just leave it soaking. And when you leave it soaking, what's called Gibbs free energy will pull the food particles off of the dish. So everything that's done has energy behind it. And in our environment, very often it's accentuated with fossil fuel, for example, that's used to heat the water. All right. I have to be very careful about doing, okay. Now we have 8 lectures that will be Monday at 8 in the morning. And this first one will tell you who I am, where I came from, what energy is, and our history of understanding the basics of energy, and end up with the laws of thermodynamics. That'll be today. It'll be about a 1-hour lecture, and then we will have half an hour for questions. The second lecture, in other words, a week from now, will be the particular role of the sun, the early Earth environment, evolution of life, green plants, and what it's meant to live in an oxygenated environment. Also, the geology of the formation of fossil fuels and the evolution of increasing biotic complexity. And then we will end up talking about, in some detail, about ecological systems and how we study energy in these systems. In other words, how do you go about understanding energy in a natural system and ultimately in an economic system? The third lecture will be the evolution of mammals, what are called proto-hominoids, in other words, our earliest ancestors, and then our own species. The increasing exploitation of energy by humans, the Industrial Revolution, and our modern situation. Then the 5th lecture will introduce you to my particular minor claim to fame, which is called energy return on investment. And then we will ask how much energy of traditional types is left for the world. And are there limits to growth? We will ask that question. Then the 6th lecture will give an introduction to standard economics. And the 7th lectures will give you my perspective on what economics should be, which is biophysical. The 8th lecture is open for general discussion. Okay, that's what this course is about. Are there any questions? Can somebody just say something so I know you're hearing me?
We hear you.
Okay, good. Thank you. Who I am. That's me. This was I guess I was 13 then or something, doing what I did most anytime I could, which is go up to Trip Hammer Pond and fish. And I was just interested in fish or water or fishing or swimming or getting a face mask and looking under the water or so forth. I was Mr. Nature Boy. And then very involved with Boy Scouting. I'm an Eagle Scout, and all my merit badges are about nature and things like that, or at least all that I had an option for. I grew up in an idyllic coastal environment of Massachusetts, Hingham, Massachusetts. On the salt water, I lived about a mile from the salt water, although I was always more interested in the freshwater environments. Here's just another picture, a beautiful coast of Massachusetts. And I'm fishing there for bluefish or striped bass, whatever would come along. Then I went to Colgate. What a lovely place this was. Colgate University in upstate New York. I don't know how I got in there because I spent, I'd read 100 books a year when I was in high school, but none of them that they were required by my classes. So that was sort of how I was. And I went down to this creek in the middle of the campus and caught a 14-inch brown trout on a dry fly the first morning I was in college. And so I was just all happy. Everything was just fine. Thank you. And I was a literature major initially because I had been very influenced by some of my English teachers at in my high school. But in one day, somebody said to me, "What are you doing tomorrow afternoon?" And I said, "I don't know, go fishing or whatever." And he said, "This guy is coming and he's going to talk about ecology." And this is 1967. And I said, "Ecology, what's that?" And he said, "Well, it's about swamps. You'll like it." And in fact, it was a Colgate grad that had come back to Colgate to give a lecture on ecology, and it transformed me. And he showed pictures of himself and his students out in a coastal environment, a Spartina grass environment with fish nets and chemistry equipment and stuff like all kinds of interesting stuff. And I thought, my God, you can do that and make a living. And so from that hour till this hour, I've been an ecologist. My life has been a straight line. Well, I guess so at about age 25, when I was probably in my master's work, I decided that there were three big things I could do with my life. I could become a good ecologist, which would be very hard because for me as a literature major, I hadn't taken all the basic sciences I had. So I had to take lots and lots of chemistry and physics and geology and all of that stuff. The second thing I looked at life as a road going away from me to the horizon. And what did I want to do with that road? And so these are the three things that were interesting to me was become a good ecologist, do a lot of fly fishing or, girls, have a family, all that stuff, which was a kind of a confused muddle to me. And I decided I could do only two of them well, and I opted for one and two. And so even though I certainly like girls, I swore off of them for about 10 years and allowed me to achieve one and two. And then I finally met this guy, great big fella, 6'4", Howard Odom, at the University of North Carolina. And he absolutely transformed my life. He taught me to think about ecology, not in terms of species, but in terms of energy. And in terms of systems of energy devices. Or, I mean, he certainly did not exclude talking about the individual species and so forth, but the focus was trying to understand ecosystems as a whole and how organisms interacted with them. So this is the University of North Carolina, beautiful place. My mother told me it was my mother, who's a Southerner, told me it was a beautiful place, and that probably prejudiced me to go there. But then when I found out that Howard Odom was going to be there, it clinched it for me. So I was a very studious graduate student, worked 60 to 80 hours a week. And initially, I didn't know what to do for a research topic, but we had these lectures every week in the biology department. And this guy, Dr. Peter Larkin, came to UNC and gave a presentation on the population biology of Pacific salmon, and I was enthralled. So that evening over beers, Odom took me and Larkin into a corner and said, "No one has studied fish migration from a systems perspective." And bang, I had my topic. And that has led to all the stuff I'm going to talk about, including economics. Now, how is that, you might ask? Well, I'm going to tell you. And so I found this beautiful stream in Duke Forest near the University of North Carolina called New Hope Creek. And I set up these barriers. You can see it over here on the right. This is my early crude one, and then I made them increasingly sophisticated. What are called weirs, fish traps. And the fish were supposed to have, at that time, were not supposed to move in streams, but I found, in fact, that they moved a great deal. And you see the weirs would funnel the fish into these fish traps. And every day it was a little bit like Christmas. I'd pull out an upstream and a downstream fish trap and see how many fish were in the trap, how many I'd caught. And I found very strong patterns of movement of the fish in the stream. And so the stream is normally clear. It's a little bit muddy on this particular day, but you can all get another view of how I'm getting the fish going up and down. And I did that for 2.5 years, and that was the basis of my PhD. And I weighed some 10,000 fish. And I also studied the energy use, the total energy use of the upstream and the downstream portions of the stream. So just without going into detail, these are my results over 2.5 years, and the fish would migrate the most in the spring, March and April. And this is the biomass in the blocks. And obviously at that time, I'm learning how to do computer graphics, which is very primitive in those days, but obviously I could do certain things. And you see the numbers are going down. The big fish are going up. You look at it this way, bluegills, for example, the little ones are going down and the big ones are going up. And we found that for most species, although I think mostly we didn't catch the very little fish because they'd go through the screening I was using, but this for all kinds of different fish in the stream. And I also, this just shows you some of the data that I get. Now, I did this 80 times. I'd go out and spend 24 hours measuring oxygen going up and down from the nighttime to the middle of the day and then down again in the evening. And this is an upstream location, and this is a downstream location. And you see that this is the way you go through and take the first derivative of this and do some hocus pocus, and then you integrate this area and get photosynthesis in this area, and you get respiration. In other words, the energy that's collected and turned into biological matter, in sugars, essentially by photosynthesis, and the total energy used by the whole ecosystem. And I found that there was a lot more intense energy activity upstream compared to downstream. And the fish would migrate into these shallow upstream areas and have a much larger energy availability for their offspring. And then many of them would move when they grew up to be larger fish downstream. It's a more complicated story, but that's basically it. And I looked at over the year the amount of energy produced and used, upper line, and produced is the lower line for this stream. So I'm thinking about ecosystems in terms of energy. And what this did was prepare me to think about economic systems, not in terms of dollars, but in terms of energy. How much energy did they produce? How much did they use? How did it change over time? How was it exchanged amongst the different components of that ecosystem? And ended up making these complicated flow diagrams summarizing my energy for the upstream environment, for the downstream environment, and the amount of energy used by fish. Now, as a fisherman, I'm used to going to a stream and thinking about the fish there, but the energy that's being used by the fish is just a tiny amount. 1% or less of the energy being used by the whole ecosystem. So that was something for me I mean, it was kind of a shock. And then we looked at the energy that's used in migration and so forth. And from this, I came up with the concept of energy return on investment. It's the energy delivered to an organism, in this case, a migrating fish, from the energy put into that activity. And I was interested to find that for every energy, every calorie or joule, just two ways of measuring the same thing, that the fish put into the migration, there would be a return of at least 5 joules to that fish and to his progeny. So I began to think about that a whole lot and apply it to other areas in ecology, which I'm still doing. And then to later, and I'll talk about this, then we began to do this for looking for oil. How much, if you take a barrel of oil and look for oil and drill in the ground and whatever else you do, how much do you get for that, and how does that change? And there's an awful lot that to learn when you start looking at society from that perspective. Now, I was also greatly influenced, well, obviously by my advisor, Howard Odom, but also by a guy named M. King Hubbard and another fellow named Jay Forrester during my graduate school. And this will be reflected in these lectures here. From Odom, I learned of the incredible importance of fossil fuel energy in society, and few environmentalists know how to deal with this issue. And why do we focus in our schools and society so much on environment and so little on resources? Now, just to give you an idea of what fossil fuel means to our society, this is a 33 horsepower harvester at the turn of the last century. So you've got 33 horses, actually mules, but 33 horsepower here, pulling this thresher. You've got 5 people sitting on this device, operating it. You've got stable boys. You've got to take a certain amount of whatever you harvest and feed your horses and so forth and so on. So all of these things are happening. Now compare that and think about this with a 200 horsepower, i.e. 7 times more harvester, and think in terms of the work it does for society. Now, when my father was born, more than half of Americans were farmers. Now it's less than 2%. And why? Well, you're looking at it. It's because we use fossil fuels. Now, excuse me for a moment, but my computer is telling me I'm getting, of course, I don't know how to get out of here. There. Let me just make sure nobody else is wanting to come in. Admit. Okay. Paul, welcome, and you've missed some, but it's recorded, so we can get it to you. Now I'm going to go back to my lecture. If anybody has any problems, let me know. Now, I go back to the lecture mode. Okay. If anybody has a problem, let me know. Now, at that time, while I was in graduate school, this very influential book came out by Donella Meadows and Dennis Meadows and others called The Limits to Growth. And this was just amazing to me because I was studying about the resources to natural ecosystems. And this book was about the resources that are for human ecosystem, shall we say, or ecosystem, the human dominated ecosystem. And this was initially Done by, damn. All right. This was originally done by this guy, Jay Forrester. And Jay Forrester invented computer memory and did this stuff on systems dynamics. And then it was his students, the Meadows and others, who took over the project of limits to growth and became, I think it's one of the most widely published environmental book in the world is The Limits to Growth. Let's see if that works. Okay. And what The Limits to Growth showed is that over time, resources would be used up. The human population would grow until it didn't. Pollution would increase, industrial output per capita would increase, and then drop off. The birth rate was declining, the death rate was declining of people, so the population would increase and then decline. And in the model, it would happen due to a shortage of resources and pollution. And obviously, we're thinking about these things all the time. So this idea that you could put in a computer model and predict the future, I mean, it was very new at that time and very exciting to me. And that's a large part of what I learned at that time was about computer modeling for mostly in natural ecosystems. But I was aware of this going on in science more generally. Then one fateful day, I was browsing in the University of North Carolina bookstore and found this book on resources and man. That was in whatever you want to call it, politically correct or properly proper use of English, resources and people. And that had a chapter by this guy, Marion King Hubbard, who was a geophysicist at the Shell Lab in Houston. And in 1956, he wrote a paper with predictions for the peak year of US oil production, which was 1970. And it happened. This was, the yellow was Hubbard's prediction for oil production each year. Now, look, I'm born in 1943, so that's where I'm born. And I'm reading that about 1970, 60, 70, 68, 69, that's when. And in 1970, it actually occurred. And this little bump was from Alaska, but that soon came down. And of course, we have another bump here from fracking that we'll talk about later. But it was astonishing that here we had built a society completely built on oil, and we were the world's largest producer of oil. And then it fell away dramatically like that. And how did we continue? Well, we imported the oil from Canada, Mexico, Saudi Arabia, Russia, etc. So we applied this energy return on investment to oil, which we'll talk about later. And it was, I got very, very involved in studying oil as an ecologist. Okay, subsequently, I did a postdoc at Brookhaven National Laboratory. I also worked at Oak Ridge. And then I was a professor first at Cornell University, then the University of Montana, and then State University of New York College of Environmental Science and Forestry, where I spent my last 30 years, and it was a wonderful place for me. Much better than at Cornell, which I have mixed emotions about. And I worked a lot on the migration of salmon and the energy return on investment of migrating salmon. So I would make these big models where you'd have the spring bloom of food. Now you can see what that means at one location right here at the Fraser River. Here is the little plants, phytoplankton. Here is the little animals, the zooplankton that the salmon eat. And the salmon come out of the rivers just at the right time to nail the zooplankton. And sockeyes in particular turn and go up along the Alaska Gar, following the bloom as it occurs up and along the coast of Alaska. And these kind of things were fascinating to me. But I lived in a world of models. That's the kind of model I was making. But I was very much involved with ecology in general, where many kinds of models were being made. And I thought most of them were, well, BS. So I spent the next 7 years studying economics, thinking that they would have better models. So that was amazing to me. I found their basis in reality even less than for ecology. So that was quite an amazing thing for me. Let me see if I can. Does that help? No, that does not help. Sorry. So I started to apply my natural science to economic issues. And here's the first paper we did this petroleum. I used fisheries concepts, yield per effort, and applied it to oil. And I found out that the same concepts that worked in fisheries worked in oil, and in fact works in copper and works in lithium, works in all kinds of things. That the harder you fish, the less you get per unit effort. So the harder you fish for fish, you're increasingly fishing for fish that have already been caught. The harder you drill for oil, the more you're drilling in the current situation, the more you're robbing oil from existing oil wells. And so that's a concept that I've thought about a lot. Now, you see, I'm thinking not of ecology in terms of how nice the green world is and so forth and so on. I'm thinking about ecology in terms of resources, both for the fish and for human society. What are the resources necessary to support the system? I was even on the first page of the Wall Street Journal. And that was, my Andy Warhol's 5 minutes of fame moment, I suppose. Although I've also been, there's been more. Some people pay attention, most people don't. And then I wrote this paper, Energy in the US Economy, a Biophysical Perspective, with some of my students. And this is in the best journal. And this is interesting. I may be the only person ever to be denied tenure at an Ivy League university on the week I had the cover issue of Science. That was the ultimate you can have, is the cover issue of Science. And this is showing an oil well behind a field of dead cars, a dead oil well in a dead field of cars, which is a little bit the message of this paper. But anyway, my life became much better after that. So, okay, we're ready to begin a study of the beginning of science. Would anybody like to speak up with a question about my life? Somebody say something so I know you can hear me.
Well, thanks for sharing.
Okay.
Why were you denied tenure?
Got me. Uh, and when I applied for the position at SUNY Environmental Science and Forestry, I was told by the people there that they called their friends down at Cornell, because there's a lot of back and forth, and said, why was Charlie Hall denied tenure? And they said, we don't know. But I met the dean. I really thought the dean was an asshole, so I don't know. The dean said it was the department said it was the dean. The dean said it was the department, but by that time I'd been there for 13 years. I'd gotten whatever I put out of there. And I tried to teach at Cornell in the personal way that I was taught at Colgate. And I was told 3 times by my department chair that I spent too much time with my students. And that simply wasn't the academic environment I was looking for. Is that a good answer? I don't know.
But
I
Charles,
have. Go
Yeah,
ahead.
yes, thank you. That was a good answer. Thank you very much.
Charles,
Yes.
not to try to correct you at all, but the peak of production in the US happened last year, 2023.
I'm sorry, what is that?
I was trying to not correct you. I'm just saying the peak of production in the US happened last year.
Oh, we're going to talk about that. Oh, don't worry.
I'm
We'll
not.
talk a lot about that.
I'm not worried.
But yes, I stand corrected. But I just wanted to make the point of what I was experiencing at that time. Oh, yes, the peak of production is just about 1 month ago. And we'll talk about that.
Okay.
Okay, now I want to make sure we understand these words. They're words from science. Empirical means derived from your senses. And it's often equated with the word data. So this is as opposed to theoretical. So you can have a theoretical, let's say Hubbard had a theoretical model of what oil production would be, and then the empirical model would be the data. So let's just go back and look at that. So the model is the yellow. See, Hubbard predicted the yellow points. So that's theoretical. And the green, and this is for the lower 48. He said, I think there might be oil in Alaska, but nobody knows. And the green is the actual production. So you can see it's pretty close, but not perfect. So this is empirical and this is theoretical. First principles is a scientific word for things that we understand for sure. And they include laws of thermodynamics, conservation of matter, and then it gets a little bit dicier, but things, Newton's laws, these are things we understand for sure. And what we would like to do is make a model from first principles, or at least that do not violate first principles. And because we know first principles are always true, at least as long so far. There are perhaps Einstein has some exceptions to Newton's first principles, but that's a very special case. And then validation means seeing if your prediction or your model is correct. Those are words to keep that I'm going to use from time to time so that we want to keep them in our mind. Okay, now let's start off with what is energy? This is a course about energy. I better tell you what energy is. Well, the answer is we don't know. Well, we sort of know. We know energy from its effects. And energy is sort of easily and inexactly defined as the ability to do work. And that means move something to cause it to be displaced from where it would be otherwise. Energy is the force that causes things to move. Where does energy come from? Well, we know a lot comes from the sun as photons, but we don't even really know what photons are. So it's probably best not to worry about that too much. Now, energy is divided into two types, potential and kinetic. Excuse me. We know forms of energy: radiation, pressure, sound, heat, and chemical. All of these we know of as energy, but they're all kind of very different things. And of course, we know the sun provides us with a lot of it. We know that the sun is, we might say, wearing out over time. Maybe the universe is wearing out over time. Maybe we think that there was a big bang with a lot of energy at the beginning, and it's been going downhill since, turning into unavailable heat. But while that happens, which, don't worry, it's going to happen for a lot longer, life has been able to intercept some of this free energy. Free means available, useful energy, and turn it in, run the machinery of life. And we know that happens even if we don't know exactly what energy is. But this energy can be captured by chlorophyll and turned into sugar and then passed along food chains, and we can have it in our breakfast cereal or bacon. So, well, we know how to measure these things, and I'll show you. Even if we don't know perfectly what energy is. Now, think about our ancestors. Our ancestors, which look somewhere between us and our cousins, the great apes. There used to be many kinds of creatures, at least 8, that were what we call proto-hominids. They were early human-like critters. Not all of them made it through evolutionary time. In fact, only one species has made it through till today. But they were clever critters that they could look at their world and increase their cranial capacity over time and figure out how to exploit it more and more. So did our ancestors know about energy? Well, certainly in very practical ways. They knew about the energy of a bow, of shooting a projectile. They knew about how arrowhead could increase that force, the work that force would do by concentrating it in the point of the arrowhead for killing an animal. They certainly knew a lot about animals, and that animals needed to eat too. They knew they had to eat. And they, at some point, learned about fire, which is another energy sort of thing. So our ancestors had a lot of practical information about energy, as do you. As I said to my students who usually did not understand calculus very well, that my dog understood calculus well, because he didn't run to where the ball was, but he ran to where the ball would be, which is what calculus is all about. Now, slowly we became civilized. And this is ancient Greece and Socrates' group, and guys started thinking very seriously about things. But mostly we attributed things going on to gods. And it's very interesting. Many of the gods were about energy. So there was the Egyptian god Ra, or Amun, who was about the sun. And, if you're going to worship anything, you might as well worship the sun, because that's the source of all the energy that runs our life, or most of it. There was Zeus, which is about lightning strikes, and lightning, of course, is about energy. Vulcan, who was the godlike or the god who worked with fire and with forging, and Prometheus, who stole fire from the gods and gave it to humanity. So many of the ancient gods were about energy. Now, in around starting 1750, was the birth of modern science and the scientific method. Maybe before that, I guess. And the first really important science came was figuring out our place in the universe. Now, Aristotle, Theophrastus was a very good botanist, had some really good ideas about plants and where they grew and so forth. And certainly they were thinking a lot about it. But major questions were about how did the planets move and did the sun go around the earth? As is obvious, you can see the sun go around the earth or something else. So the first guy to think about this in some detail was Ptolemy, who was a Sicilian who lived in Alexandria, which was the intellectual Alexandria, Egypt, which was the intellectual capital at the time. And he promoted the motion that predicted the motion, for example, of the planets. And he made tables where you could predict far into the future using mathematical equations where Venus and Mars and the various planets would be. And he thought the Earth was the center of the universe. Very arrogant perspective, I suppose, from today's view. And that the planets and the sun went around us. But he was bothered by this, what's called retrograde motion over the course of months of Venus and Mercury, the inner planets. So he came up with what are called epicycles. So if X is the Earth, and I guess this circle is the moon, or maybe the sun, I don't know. But he has the Venus and Mercury going around in epicycles. And these people were all sort of led off track by thinking that all the planets traveled in perfect circles, including the epicycles. See, this is going round and round as this is going around. And he derived the math, which is quite impressive, to make this work and make the prediction of the planets really good. This is in, I don't know, 100 AD or something. And so, and he could make very good predictions, and people thought it was important to predict where the planets were because they thought that that would control whether it was a good time to make a military campaign or not, or whatever. And so a lot of astronomers were hired by kings and empire leaders and so forth to help figure out what should be their, when they should have military campaigns or other sorts of things. Now, this is a fantastic book I read last year called Tycho and Kepler. And Tycho Brahe built an observatory in Denmark. He built several of them. And as you can see, it's a whole building. And he'd have a little hole in the wall, and then he could look at the sun or the stars or planets, I suppose, especially planets. The whole thing would rotate, and he could do a very careful derivative of where the stars and the planets were. But he didn't have good enough math to figure it out exactly what it meant. And that came down to a guy named Kepler. And Kepler was the guy who figured out that the planets went around the sun, including the Earth. So Brahe went to his grave, even with all this enormous data that he had, he went to his grave thinking that everything went around the earth, the sun went around the earth. And Copernicus was the first to say, well, both Kepler and Copernicus worked out together that the planets went around the sun, including the earth, and they're all, and how you do the calculation, you can only find in the notes in the back of this book. It's much more complicated than I understood. But anyway, this was the beginning of real science. And the interesting thing was, you could make a prediction from Ptolemy, remember that Egyptian guy? You could make better predictions from his model that had the Earth at the center of the universe than you could with the correct Copernican model, because Ptolemy was such a good mathematician. And as a model builder, I was always interested in that, in economic models. You could make, for example, the University of Pennsylvania model of the economy is very, very accurate, but I'm sure is based on the incorrect principles. But it's still so accurately parameterized that it can do well, at least for 1 year into the future. So that's an interesting question we'll discuss. Then along came Isaac Newton and showed that there were energy principles that could be expressed mathematically. His 3 laws of motions, his law of universal gravitation, these are just so beautiful and so elegant for understanding energy and understanding things in general. We could shoot our first rocket to the moon. We could shoot it using Newton's principles and without even making a mid-course correction. His equations derived in 1560 or something were so accurate that we could use them in 1970 to shoot a rocket to the moon. Amazing. So science was progressing, but our knowledge of energy in 1800 was very confused. Heat was thought to be a substance, phlogiston, that flowed from hot objects to cold ones. The Industrial Revolution was just starting with the Newcomen engine. Just to show you how it worked, you have a steam boiler here. This is the first steam engine. And you'd make steam and you push a cylinder up, and then you squirt in cold water, the steam would condense, and the atmosphere would push the piston down, which on the other side of this rocker arm is lifting water out of the well, out of the coal mine. Actually, these great big devices saved the coal mines in England, which were flooding, because they could do so much more work than the horses could. That they could build, 50 horsepower steam engines and burn coal to do that. But the first guy that came along to understand what was going on was a guy named Benjamin Thompson, or Count Rumford. And what he's doing here is, this is a cannon. They're boring a cannon. And when you're boring the cannon, you're generating heat. See the heat coming out here, and he would dull the drill so it wouldn't drill the cannon. It would just go round and round and make heat. And he could keep doing this for weeks, and he'd never run out of what was previously called phlogiston. In other words, that he was the first to understand that heat wasn't a substance, as people thought at that time, but was something else, which we eventually figured out heat was the motion or the activity of molecules. But they were very confused for a long time, until they began to realize that what was important about energy was a gradient. it's the difference between heat at a high temperature and heat at low temperature that allows work. And it was this guy, Sadi Carnot, who was a French military engineer, published 30 copies of this little book that for the first time allowed us to understand energy, which was found by accident in a bookstall on the shores of the Seine, the last copy known to be in existence, and he laid it all out. And what was important, he said, was the gradient in heat between hot and cold. You needed both to make a machine work. The next important guy was James Prescott Joule. We honor him with our units of energy now, joules. He was a brewer, but had a very curious mind. His ideas initially were put down by the upper class, which were most of the scientists at the time. He was, quote unquote, just a brewer, but he was very clever, and he spent his whole life basically improving this machine. An insulated box containing water in a paddle wheel, and you see you can drop a weight, do 1 foot-pound of work or 1 meter kilogram of work, and turn the handle, and ignoring heat, ignoring friction at the joints, you can measure with a thermometer how much the water increased, and you began to understand that there was an equivalence between physical work done and heat generated. So that's how we measure all energy now, is we turn it completely into heat and measure the calories. That doesn't tell us other things about the properties of the energy, but they are all interconvertible to heat. And finally, Sir William Thomson, or Lord Kelvin, he said, hey, this guy, Joule, is good. And it became accepted in time because this guy was a lord. And then they began to understand the implications of Joule's theory over time, and thermodynamics was born. And Thomson came up with the second law of thermodynamics, which I'm going to explain in just a moment. Well, here it is. These guys, Thomson, Rudolf Clausius, Hermann Helmholtz, and Kelvin, gave us the laws of thermodynamics, means heat changes. First law of thermodynamics, the quantity of energy is conserved, and it's conserved as heat, because all transformations eventually, at each transformation, some is changed into low temperature heat, which is from which you can get no further work. But the second law of thermodynamics says the quality of energy is not conserved. At each transformation, some energy is lost to low-grade heat. What that means practically is you cannot recycle heat, and we're going to run out of energy eventually. Not tomorrow, but eventually. So these, when they were formalized, they help us understand energy a great deal more. And of course, other people came along, Faraday, Maxwell, Steinmetz, and Einstein, of course, but these are not important ideas for this course, although we can talk about them if you wish. And we end with my final professional goal, which is to push this boulder off the cliff, but that's going to take us another 6 lectures to do. The end of this lecture. Now I got to try to get back to people. And I'm not quite sure how I do this. This is the end of lecture number 1.
There might be a stop sharing function.
No, I can't see anything. I can't see anything on, oh, I just found something and it disappeared again. I'm
Move your
clicking on my
cursor.
Zoom button.
Does it appear when you move your cursor?
No. view. Let's see, wait a minute. View, let me try that.
Are you on a Windows or a Macintosh
I don't
machine?
know what I'm doing. Refresh. No?
Are you on a
I'm
Mac or
PC.
a PC? Okay.
And I click on Zoom, I click on Word, and nothing. Let's try clicking on the PowerPoint. No. No,
It's
have you
that the-
been looking at this picture? It looks like people building structures into anthills or something.
I'm looking at Jay Forster.
Yeah,
Well, I'm
we're
not.
seeing the slide with Jay Forrester on it.
How
My
about
other
refresh?
My other experience with digital usage is that you gotta go slow. You gotta give it a second to do something. If you do it too fast, it gets confused. If you do it
Yeah.
twice in a row, it gets too confused.
Try exiting your full screen. You might get some more options.
I don't even have an X to get out of it. Here's a
Well,
view.
You are.
in order to
mine-
get out of this, you really want to stay, you don't want to go over to Word. You want to stay within Zoom to find your way to stop
Oh.
sharing.
Well, I click on Zoom, and for a second, it
Get
showed
your
me the,
cursor down at the lower part of the screen and see if you've got any choices that relate to sharing.
oh, wait a minute, I got something that says Zoom. I click on that and nothing happens. Somehow I've got this. Oh, oh,
You're-
oh,
You,
What
you
was
are
that?
sharing. I'm viewing your screen.
yeah. Well, we can go ahead. Who's got a question? And I'll try to figure out what to do here. That doesn't do it.
Do you have an escape key?
Yeah, I've been pushed that 25 times.
I don't have a question, but I have a comment, which is,
Yes.
I too read Limits to Growth when I was in college
Yeah.
and was very much influenced by it. In fact, it made me choose modeling as a career myself.
Oh, really?
And I just wanted to comment that there have been updates to the Limits to Growth
Oh, yes.
by
And I've written
by
some of them.
some of the co-authors, and you perhaps contributed to that effort, but it's still a very, I think, very active and very influential body of work, and it keeps getting updated. So I think that really, and there are lots of ideologues that criticized Limits to Growth after it was published for being way too negative and pessimistic about the future of capitalism and the future of possibilities of growth, et cetera. But I think that right now there's a wide acceptance that yes, there are limits to growth. And the question is, when do we hit those limits? And so maybe they were a little bit pessimistic in forecasting the timing of when population might decline. But if we're not careful, we're going to hit some limits that might be quite challenging for the human race to deal with. Anyway, that was my comment.
Oh, yeah. Oh, excuse me. I can't see you because I can't get out of where I am here. But, oh, wait. This is looking, there we go. Who is speaking, please?
Oh, Carl.
Carl.
Yeah.
Carl, well, I just sent you an email for a different matter.
Yes, thank you.
And incidentally, just while we're here, I want to come back to your point. But very much well, this, we're supposed to have an assistant for this class, somebody who will help me. And your name, Carl, was suggested by Ann Coleman. I don't know if you
Oh,
know her.
uh-huh.
But
I'm
I would
a-
like to ask if anybody, Carl or anybody else, might be interested in that job, shall we say.
I would be willing to, except I'm teaching a class this quarter and I've got to really kind of focus on that, unfortunately. And I'm not as technically savvy as you probably
yeah.
would like your assistant to be.
By the way, you stopped sharing your screen. Do you know how you did that?
Yes,
Charles?
I clicked stop sharing.
Okay, did that just appear really recently? Or did you have that
No,
before?
that was deliberate.
Okay,
That was deliberate.
So I have a question
So-
about population dynamics.
Yeah,
So
excuse
if-
me, may
if
I
you-
answer Carl's question
Oh,
first?
sure.
Carl, you've got my email because I sent you an email. So I will send you, I guess I have yours, come to think of it. So I will send you, when this is done, I will send you 2 papers that I have written. Well, I will send you 3 papers that I have written on limits to growth.
Oh, okay. Thank you.
I know Dennis Meadows quite well, personally. And I agree very much with what you say, that this is still a very much active issue to deal with. Okay,
So a
now,
question about,
Jeff,
yeah, population dynamics. If you put some bacteria in a petri dish with plenty of nutrients, they kind of overpopulate and then die. So the question for humans is, we have countries, let's take Italy or South Korea as an example, where they have plenty of resources and plenty of food, and you would think that population growth would just kind of go exponentially up like it does with most other species. Why did it peak and why is it going down? And why are humans different in that respect from most any other species?
well, let me give you my short, I don't want to call this a male chauvinist view, but it may be labeled as such. I think that people like to screw, and children are often not planned, but a consequence of the first thing. And when women are given a choice, in which I completely believe, they often do not want to have as many children as they historically have had. Bach, for example, Johann Sebastian Bach had 20 children. And you look at the lives of our founding fathers and mothers, and they often had a dozen or more children, many of whom would not survive. And we're going to look at human population growth over time relative to energy. What were the 2 countries you mentioned?
Italy and South Korea currently have some of the lowest.
Well, Italy is
replacement rate.
curious because its resources are limited. It imports most of its fossil fuels from Africa. Italy has very, very low fossil fuels. I mean, of course, what Italy has is very clever Italians who but were their resources? It's a moderate agricultural area. The Po Valley is very productive. But most of Italian food production is modest. The seas around them have been overfished. They're very, I knew at one time the chief admiral of the Italian Navy, and his job was to protect the LNG, the liquefied natural gas ships that came in from Algeria and Libya and so forth from terrorists because, one well-placed torpedo could take out a big city like La Spezia or something like that. So Italy is very dependent upon African resources in many ways. But of course, what they do is they have very clever engineers and etc. I can tell you a good story. I don't know. I want to. Well, I took my mother. My mother and I both like opera, and I took her to Aida La Scala. If you know anything about opera, that's the ultimate. And we had shared a box with a German industrialist and his Italian girlfriend. And I asked him why, what he was doing in Italy. And he says, well, this was in 1990 or so. He said, Italy is a great place for an investor, for a financial guy. I said, why is that? And he said, well, when we had the energy crisis of the 70s, and I guess you're probably old enough to remember that, it was a big deal. England went after North Sea oil, which is good, but it's expensive. And France built all these nuclear power plants, which are good, but were expensive. And Italy characteristically did nothing. And now the price of oil has come down again. We import Italian oil, and we can make things in Italy much cheaper than France or England. So I don't know if I'm giving you a good answer, but I'm at least giving you some good stories.
Well, just as a addendum to what you just said, cheap energy is foundational to a successful economy. And one of the great advantages that Germany had and made it the economic engine of Europe was access to cheap energy from Russia, oil and gas. And that competitive advantage has now been lost to Germany, and Germany's going through a very wrenching readjustment that's causing it is now in recession because of the war with Ukraine and the probably permanent lack of access to cheap Russian energy. So energy is key to the wealth of nations.
Well, I certainly believe that. But it's more complicated than that because obviously, fossil energy is a two-edged sword. But yes, I agree with that very much. And I'm going to talk later in class about what the Europeans call secular stagnation. Their economies now are not growing or are barely growing. And that has been the case for almost a decade, in Japan also. And their energy resources have also ceased growing. So what's the chicken and what's the egg? And we'll talk about that. And we're going to try to take the long view of those questions. Okay, what about anybody else? And did my lecture come through more or less clearly?
Yes.
Okay.
Thank you, Charles. Time for lunch.
Well, I'm technically we got 6 more minutes, so I'm gonna stick to the schedule. It would be good. Anybody have another question for the moment? How about entropy, thermodynamics, anything like that?
I have a comment. It's interesting how your career has paralleled mine. I was involved very early on in fisheries management with the Department of Commerce in 1977, 78, when shortly after the Magnuson Act was passed, and suddenly to manage fisheries, they needed these fishery management plans, which entailed a lot of modeling of growth rates of stocks and what the optimum yield could be. And then
Yeah.
I went on.
Maximum sustainable yield.
Yes, yes. And
Did you
then
read? Go ahead.
eventually I ended up at the Bonneville Power Administration, which does a lot of funding of salmon recovery efforts in the Columbia River watershed. And so the relationship between hydroelectricity and salmon is very strong in the Pacific Northwest.
Very strong and negative.
Yeah.
But you know, the only free-flowing portion of the Columbia River now is Hanford.
Yes, right.
Have you ever read the article by Peter Larkin, an epitaph for maximum sustainable yield?
No, I haven't. I've been kind of out of that for a while.
Well, you might enjoy reading it. Peter Larkin, Larkin,
Okay.
and an epitaph for maximum sustainable yield.
Yeah. Okay.
And let's see, you're the one I'm going to send material on the limits to growth.
Yes. Yeah. And of course, with all that modeling and regulation, fisheries are still in trouble.
Yeah, I mean, the basic, I remember Arthur Hassler. I don't know if you knew him, but he told me once that in a perfectly managed fishery, then you would catch, how did he put it? You would catch all of the net production. But then Jack Downing, not as famous a fisheries guy, but one of my favorites, wrote a paper that said there is no fishery that has been sustained where you have taken more than 5% of the net production of the fish, that somehow we thought we could take half of it, more or less. Rickers and stuff. You probably know about rickers. And we could take half of it or so, but we can only take 5%. Looking empirically, there's a good example of models versus empiricism. Anyway,
Yeah,
there you are.
I think we tended to look at each population in isolation, but population, there are impacts from overharvesting, not just because of the population within a species, but then there are cross-species impacts. And you completely affect the food chain across the ecosystem, right? And
Yeah,
in
and so
ways that we
I
don't
was an
fully understand.
ecosystem scientist, and I would argue with population scientists on those kinds of arguments for a long time. Terry has just joined, I think, and if he's missed this lecture, I have recorded it, and it should be available shortly. Where do you live, Carl?
I live in Ashland now, near the SOU campus.
Yeah, well, not very far from me, a mile or two from me. We should have a beer sometime and talk
Yeah.
about fisheries modeling.
Yeah, that would be fun. Yeah, we should.
Terry,
Hi there.
did you just join us?
I did. I've spent all this time trying to get in. I've been in the waiting room
Oh,
repeatedly.
well, Terry, I've recorded this.
That is fabulous.
So, but I can give you last year's opening lecture, which is more or less the same thing, immediately, or I can, let's let's see, will you send me an email at chall@esf.edu?
Sure, will do.
Chall, CHALL @esf.edu. Gosh, I wonder if there are others that had such a problem.
This was a first for me.
Okay, but we'll take care of you, Terry, just fine.
Okay, cool.
Okay,
So in the future, the class starts at 10:30.
well,
and-
no, you can come in anytime between 10:30 and 11.
Oh,
10:30
okay,
is, the door's open.
got you. But the class officially starts at 11.
Yep.
Okay, thank you.
Okay, now it's 12:30. It's time to end class. Goodbye, everybody.
Goodbye. Thank you
Thank
for the
you.
class. This is
Yeah,
going to be
thank you,
fun.
Charles. This is
Okay, good.
fascinating.
Thank
Well,
you.
good. I don't
Thanks.
have quite as many people as I wanted, but I think I got some good ones. Okay,
now.
bye-bye.
Salud. Bye-bye.
Bye-bye, Rob.